that was not the correct beginning. So today I am going to talk about geometry proofs and how we can, I guess, transition from algebra 1 to geometry. And now, first order of business, I guess, is a very quick introduction of myself. So I am Zhao Dong Cai, as you can see my name from, I guess, the Zoom camera. And I am actually one of the teachers teaching geometry this summer. And I see that some of you are probably actually my students. So thank you for coming here today. And so first order of business after my introduction is why do we still learn geometry at this age? Because it almost seems like we've been learning geometry forever since elementary school and then in middle school. And now, again, why are we learning geometry almost nonstop? Well, the thing is, we are actually learning quite different things in, I guess, through all of our years. And the first thing I guess I want to talk about is then the thing covered in high school geometry is actually quite different because we have studied geometry since elementary school, but the things we studied are mostly about, ultimately comes down to knowing various properties and then remembering a few formulas, most notably about formulas concerning area calculation and volume calculation and so on and so forth. But we have not learned why those properties are true and how those properties are derived. Okay, and maybe people can tell me, when did we learn this? People type in chat, when did we learn this? When did we learn this? People type in chat. Kindergarten, kindergarten. Sounds reasonable. Sounds reasonable. High school, yeah. Okay, okay. Third grade, kindergarten? Okay, okay. Before you were born, too long? It's been too long. Yeah, I agree. I agree. It's been too long. You forgot? Yeah, I agree. I agree. So, in fact, you guys probably all have actually learned it in elementary school, I would say. Probably, maybe even earlier. But elementary school, you guys probably have already learned all this. All right. And what about this? What about this? When did you guys learn these formulas and these shapes and the area and so on and so forth? College? I don't think so. I don't think so, Nathan. Yesterday? Yesterday? I wonder. In school. I agree, in school. For sure, for sure. But when? Second grade? That's kind of fast, man. That's kind of fast. Okay? Thank Academy. Okay, thank you. But when did you learn? Not where did you learn? Okay? Sometime in your life. Very correct, very correct. But okay, normally you guys actually learn these things in middle school. Okay, in middle school, zeroth grade. Not sure that's a grade, but we actually learn these things in middle school. Okay, and now when did we learn this though? Okay, when did we learn this? People, new question. When did we learn this? 2 days ago? Okay, that sounds about right. That sounds about right. A few days ago, yes, that I agree. That I agree. And here, the statement is rump is a square. Now, we didn't quite learn this, okay? But the format, I guess, the proof given here is essentially learned somewhat a few days ago. And yes, rump.
What
And
month ago?
2 days ago, okay. All right, cool. Thank you. And this brings me to this point, okay? So what's covered in high school geometry? Well, a lot of it is actually about proofs, okay? Proofs. So now that brings us to this very natural question, namely, so what are proofs? Now, what are proofs? So proofs, what I want to say is they are basically just mathematicians' way of convincing people, okay? They are just mathematicians' way of convincing people. And now, elsewhere in life, people might convince others using data, examples, experience, but those are not enough. Those are not enough in mathematics. Okay, what mathematicians do, what's happening in math is that every argument has to follow from some kind of definition, some kind of axiom, and then some kind of theorems, possibly. And now just to, I guess, contrast mathematics with real life. Prove it to me. Why? Okay, why Taylor Swift is the best singer? People. She's not. She's
That's an opinion.
okay. Now, some people can try to, give an argument for this statement, though. Some people might say, "Wow, she's touring the world right now, and her concerts go for like the most profitable in history, and so on and so forth." And she has had, quite a few hits in her life, and those are all great arguments for why Taylor Swift might be the best singer. But those things are all essentially based on history data, or I guess examples. Those are not going to suffice as mathematical proofs. Okay, these are not mathematical proofs. Now, but in any case, what are proofs? Proofs are essentially the process of finding reasons to back up our conclusions. Okay, this is actually true either in mathematics or across, I guess, elsewhere in life. And now here, I want to remind you, I guess, walk you guys down the memory lane. And let's think about this statement that we have all definitely learned in Algebra 1, okay? In Algebra 1, you guys for sure, okay, for sure have learned that negative of -1 is equal to 1. But why is it true? You guys probably just accepted this as one of those facts, right? You just remember that negative of -1 is equal to 1. But why is that true? Well, in fact, a more basic question, okay? What does putting a negative sign in front of another number even mean? Yeah, okay. You guys are all saying now two negatives make a positive. I agree. But how do we prove that? How do we prove that? And that brings me to this first question, namely, what does it mean to put a negative sign in front of another number? Okay? And this question further comes down to what's the definition of negative sign used here? And I see that Nathan is raising his hand. So Nathan, what's your question? Do you have a comment to make?
Can I prove it that if you put a negative in front of a number that becomes the opposite?
Mm, maybe hold on your thought for a second, okay? I am actually going to introduce a proof. I think it's going to be slightly different from yours, but we can hear about your proof in a little bit, okay? Okay, in any case, what I want to introduce to you is this thing that, well, there are, things to ponder about. Namely, do you guys really know the definition of negative sign used here? Now, what does it mean to put a negative sign in front of number? What is the resulting number? Okay? And ultimately, you guys might even, start wondering something very philosophical, namely, what's the definition of definition? What's the definition of definition, people? Kind of tricky, kind of a brain scratcher. And now here, so this is essentially my solution to the last question, namely, what is even the definition of definition? Okay, so definition in mathematics, well, basically means name for things, and that is actually also true elsewhere elsewhere in life, I guess. But more importantly, in mathematics, definitions are definitive, okay? What does definitive mean? Well, it means once a concept is defined, okay? Once we have given a definition, then we should be able to tell whether a thing little x is capital X or not. And this little x cannot be both capital X and not capital X. So in particular, when we were considering, Taylor Swift as a singer, some people might say she is a good singer, some people might say she is a bad singer, and as a result, she can be, both a good singer and bad singer, and that is not allowed in mathematics, okay? Either something is X or something is not X, and this is the point of, I guess, definitions in mathematics. Now, another thing I need to introduce is, so what are axioms? I said that mathematical proofs are all based on, definitions, axioms, and theorems, right? So what are axioms? So in mathematics, axioms are simply statements that we accept without justifications. Okay, we think of these things are just true. We are not going to prove them. And well, it turns out, for example, one of the axioms, okay, one of the axioms of numbers say that for any number x, we have x plus 0 is equal to x. Okay, so x plus 0 is equal to x. That's one of the axiom, very reasonable, and you guys are probably going to accept that as truth without and well, not requiring any kind of justification. And now here I can finally introduce to you guys what does putting a negative sign mean in front of a number. So what's the definition of negative x? Namely, what is this number? Well, it turns out to define that, I need to actually explain one of the axioms we need when we are studying numbers and so on and so forth. And based on that axiom, we can give the definition of what it means to put a negative sign in front of a number, I guess in this case, x. And the axiom we are looking at is that given an arbitrary number x, okay? Given an arbitrary number x, the axiom says there is another number y such that x plus y is equal to 0, okay? That's our axiom, okay? Kind of obvious, isn't it? That's why we are making it an axiom. That's why we accept it without any kind of proof, without any kind of justification. And now we are going to give this special number y a name, okay? And I see that people are asking me to prove the axiom. Well, that's missing the point. You see, axioms are precisely statements that we do not prove. We simply accept them as truth. And in this axiom, while this number y that adds x to become 0, we are going to think, well, this is kind of special, and we are going to give it a special name, and we name it negative x. Okay, so if I were to, I guess, summarize what's happening here is that, well, we have x plus this very special number, which we are naming negative x. When these two are added together, we are going to get 0. Okay, we are going to get 0 when we do x plus negative x. And now, finally, I can state I guess, the exciting thing, namely, how do we prove negative of -1 is equal to 1? How do we prove that? Well, here, of course, everything is going to be defined to depend on axioms and definitions and so on and so forth. And how does it depend precisely? Well, here, the steps we are taking is, by definition, what is minus of -1? What is minus of -1? Well, the definition says whenever we put a minus sign in front of a number, in this case, the minus sign is in front of this number -1, then the defining property, okay? The defining property of the symbol is that when -1 is added by this new number, okay? When -1 is added by this new number, we should get 0. That is actually our definition of putting a negative sign in front of something else. And based on this equation, based on this thing equal to 0, we are going to add 1 to both sides, okay? Add 1 to both sides of this equation. And if we do that, what are we going to get? Well, we are going to have 1, okay? That's the one we are adding to both sides. And added by this old expression is equal to 1 on the other side. And now what we are going to do is we ponder about this equation. Okay, we are pondering about this equation, and we see that, the first two terms we are dealing with here, namely 1 plus -1. That expression seems very familiar to the thing we have seen before, namely minus. This is precisely the expression we have seen in the definition of negative sign. And here we are seeing that 1 plus -1 here. And what are we going to get? We are going to get 0 as a result, okay? Because in the definition of negative sign, we have said that the defining property of putting negative sign in front of another number is that that original number, when added by the negative sign with that number, is going to give us 0. Therefore, what we are having here is simply 0 plus this negative minus 1 equal to 1. And as a result, we are going to get, after simplifying this expression, what we are going to get is essentially 0 plus negative of minus 1 is equal to 1. And what's happening is, well, then what is this expression doing? Well, the expression is just 0 plus something is equal to 1. And remember, previously, I introduced to you guys one of the axioms about numbers is that 0, when added by anything else, is going to give back that something, that anything else. Okay? And as a result, what we are getting is negative minus 1 is equal to 1. And there we go. We have proved minus 1 is equal to 1. Okay? We have proved two negatives makes a positive, essentially. Okay, so what's the takeaway here? Well, this is how, I guess, proofs are constructed. Okay, so every sentence here, every statement we are making here is actually based on some kind of definition, some kind of axiom, and some kind of theorems, I guess. So now you can actually make some complaints, namely by being annoying, which is in mathematics called being rigorous. Namely, there are a few questions here. Namely, why can't we add 1 to both sides? And secondly, why can't we, do the first addition first instead of doing the second addition first? Does the order matter? Does the result change if we do it the other way around? And in fact, if you are very, very careful, you are going to see that in the previous slide, I did something like 0 plus another number. But in the axiom about, 0, what I wrote was x plus 0, and the order is slightly changed, okay? So why are these things correct? Well, it turns out, all is good, because it turns out there are a dozen axioms that we accept about numbers that I'm not going to list, but they are going to safeguard our argument. And the proof that I presented that we were talking about is actually correct. And now here we are going to look at another example because in the previous example, we need like a dozen axioms to make things work. So that's a bit confusing because to introduce all the axioms is going to be tedious. So here we are going to look at actually another example, a very simple example, because here the number of definitions we need to deal with and the number of axioms we need to deal with are a lot fewer, as it turns out. So here, what we are going to do is consider this strange function, okay? So here, the function is defined as, say, f of n is going to be 3n plus 1 if n is odd, and f of n is going to be n over 2 if n is even. Now, the question we are going to pose is that if we start with n equal to 5, okay? If we're starting with n equal to 5, and we apply this function repeatedly, how can we prove that we are going to get 1 eventually as the result, as the output? How do we prove that? So maybe first of all, what is f of 5? People, what is f of 5? Type in chat. What is f of 5, people? So the definition of our function is 3n plus 1 if n is odd, or n over 2 if n is even. Yep. Absolutely. I see answers are streaming in. Yep. The answer is 16. Thank you. And I see some people are just spamming, but thank you. The answer is 16, okay? And what this question is asking is essentially, well, in the first step, we are getting 16. Then we are going to apply the function again to the result, namely f of 16, and we calculate that. And then we calculate the f of the result again, and so on and so forth. And the question is asking, can we get 1 in the end as the result? Well, yes, we can. And we can actually give a very simple proof. Okay? We can actually give a very simple proof. What is the proof? Well, the proof is very simple. Namely, we are going to start by saying, since 5, okay, 5, the starting input is odd. when we evaluate f at 5, we are going to use the rule 3n plus 1. And the result, of course, is going to be 16. And then we are going to apply f to this value 16. And that means we are going to calculate f of 16. And because 16 is even, we are going to get 16 over 2 is equal to 8 and so on and so forth. And then we are going to end up having f of 2 equal to 2 over 2, which gives us 1. And there we go. We have obtained 1. Okay, some people are complaining this is just evaluation. This is not a proof. But yes, it is a proof. Evaluations can be proof. If the thing we are proving is just evaluating something, then yes, we have achieved proving that we are obtaining 1 in the end. Okay. All right, and some people are actually, giving me giving me the punchline. So actually a hidden story behind this, and we are going to look at that in a little bit. Okay, in a little bit. All right. So here, this is actually one of I guess a good argument to prove that if we start with 5, we are eventually going to get 1. Okay. But even in this very simple situation, there are some, horrible proofs. And we are going to look at some, not so good proofs. And now, first of all, I guess I want to summarize why the situation is simple, why the proof is also very simple. Because, well, there are very few definitions we need to understand the situation. Namely, we need to know what is an even number and what is an odd number. Because, we need those to understand when to apply which rule of this function f. And also, very importantly, there are only 2 rules to follow, namely the 2 cases for the function. Okay, when the input is even, we are going to apply one of the rules, and when the input is odd, we are going to apply the other rule. And the simplicity given here, namely the how few the definitions are and how few the rules are, it makes the situation very easy. And to prove that starting with 5, we are going to end up with 1, we just essentially follow the notes, and we obtain a great proof. But there are some bad proofs, as I said. And we are going to look at this one. This is a horrible proof to show that when we start with 5, we are going to end up with 1. Because what does the proof say? Well, the proof says, since we are dividing by 2 at some point, the number gets smaller, so it has to reach 1. Now, there are just so many problems with this argument. And why is that? Well, for one thing, what is this argument even based on? Now, in mathematics, all the statements, all the things we write down should be based on axioms, definitions, and theorems. But whatever is written down here, there's no. It's somewhat based on common sense, somewhat based on I don't know experience, sometimes based on intuition. But some
嗯，
people
好
are
小
saying
哦。
dividing by 2. Some people are saying dividing by 2. But you see, it's at some point, but it doesn't quite make sense for all situations because the number can actually also get bigger too. Namely, what if the number hits odd at some point, and then when we apply the rule of this function f, we need to do 3n plus 1. And as a result, we are going to get bigger numbers. And furthermore, it doesn't really explain why, the numbers we are getting is not jumping between 2 values that's not equal to 1. Here, jumping, of course, I mean either I guess become bigger and become smaller, become bigger and become smaller, and so on and so forth. Why is that? Well, it's not justified here. Okay, it's not justified here. And let's look at another, I guess, proof, namely here. That's a very succinct proof, if you will. So here it just says f of f of 5 is equal to 1. Now, this is technically a correct proof because ultimately what we did before in the good proof, we are actually getting this expression, but not quite sure I can follow the steps here. Okay. Not sure I can follow the steps because, for example, it's not clear to me f of 5. I cannot do that mental arithmetic in my head, I guess. I guess I can, but still, it's not that clear. What is this argument even? Right? And no, 5 to the 5 is equal to 1. That's a weird thing to write down. No, okay? But in our case, in the previous, in our definition of this function, it turns out this is correct, but still, this is not a good proof because there's just a lot of details left out. All right. So, what are proofs? Well, proofs, as I said before, are arguments to convince people. So you should, okay, you should write in full sentences with math symbols blended in because after all, we are proving mathematical things. All right, mathematical statements. And secondly, more importantly, maybe, is that it should be clear, okay? In each statement that you are making, it should be clear what is the basis of each conclusion and what is the theorem slash axioms used. And let's go back to the good proof, so to speak. The simple proof that we have seen. If we start with 5, then we are going to end up with 1 in the end. So what was the proof? Well, it's given here again. And the first sentence, the first claim we made is that since 5 is odd, we can evaluate this function at 5. And the rule we are going to follow is 3 times 5 plus 1. And the result we are getting is 16. And we essentially just follow the same paradigm and we say, what is f of 16 and then f of 8 and so on and so forth, all the way down to f of 2, and we get 1. And that's our goal. We are trying to obtain 1 in the end, and we did. So here, whatever I labeled in blue are the conditions of each statement that we are making. Okay? So the first statement is that 5 is odd. That's a condition that 5 satisfies. We know what odd numbers means, and 5 is an odd number. And we are saying when we evaluate f at 5, we are therefore going to use this rule. Okay, this is the theorem slash axiom we are using. Namely, we are saying f is given to us as one of those defined in this way, and this is the rule we are going to follow as a result. And essentially, the rest follows similarly. So that was the situation. But you see, the situation in geometry and algebra 1 is kind of complicated because what we have just seen, namely f of 5 and so on and so forth, that was a very easy situation. In algebra 1 and geometry, there are so many axioms, and they are not actually spelled out in the book. So which statements are axioms and which statements can we actually use in our proofs, in our homework? Well, the rule of thumb is the following, okay? If a statement you know has not appeared in the lecture, okay? If the teacher has not used the statement that you know, then you should not use it. So, for example, I know some of you, actually, many of you have just finished a class on parallelness. So parallel lines in particular. And in the homework, some of you are actually using the fact that the sum of interior angles of a triangle is 180 degrees. Now, that is true. That is a theorem that we can prove. But in the first lesson, we actually have not proved that. So in the homework, you should not use it, in fact. Okay? But it just means there are actually ways to circumvent that. And you should come up with a solution that does not require or rely on the fact that's not proven so far. And here, I want to end the 3n plus 1 with this after story. So can we prove, okay, can you prove, in fact, can you prove any positive integer n after repeatedly applying the function f, we can always obtain 1. Namely, so what was the rule? Well, whenever we are given an even number, we can divide it by 2. And whenever we are given an odd number, we are going to do 3 times that number plus 1. Okay, 3n plus 1, namely. And the question I'm asking is, if we start with an arbitrary number, can you prove that we are going to end with a 1? Can we always obtain 1? Well, it turns out that's kind of hard. It turns out it's kind of hard, okay? It turns out nobody knows how to prove it. And it is actually known as the Collat's conjecture. And I guess I'll just say, okay? I'll just say that If you prove it, okay, if you prove it, you will absolutely get a PhD in mathematics. And if you prove it before you are 40, okay, if you prove it before you are 40, you are absolutely going to get the Fields Medal, which is actually the highest honor in mathematics. Okay, let's prove it, right? Let's prove it. Yeah, you can do that. Absolutely. Try to do it. And that's the after story of 3n plus 1. And now, now that we have talked so much about proofs, now let's get back to geometry. So what's so different about geometry? Well, geometry is kind of a loner in the sense that there's no, I guess, subsequent classes about geometry after you are done with geometry in high school. That is because the situation is very different than algebra, because for algebra, you take algebra 1, then algebra 2, and then you are going to learn pre-calc and then calculus and so on and so forth. There are so many algebra classes, but geometry, in particular, plane geometry, is just, a single subject by itself. And the reason, I guess, why that is the case is that, well, geometry is considered the best place to learn, I guess, logical reasoning. And one reason why that is the case is that the number of axioms we need for geometry is actually relatively few. And because as a result, the situation is relatively easy, and it is the best place to learn logical reasoning and proofs as a result. Okay. And another thing is geometry is actually very important. Why is that? Well, because in algebra 2, for example, you guys are going to spend a long time study trigonometric functions. And the trigonometric functions ultimately are geometric in nature. All right. And in pre-calculus, you guys are going to learn polar coordinates and vectors and so on and so forth. And all those things are actually based on geometry. And calculus, there are actually, some geometric proofs. And when you guys start learning, calculating volumes of rotational bodies and so on and so forth, those are ultimately all geometry. And this is also where you are going to learn or prove, for example, the formula for volumes of sphere or area, surface area of a sphere and so on and so forth. And what are some key concepts to study in geometry? Well, the key is actually the geometric proofs, okay? And because that's actually one thing that's going to be relevant throughout all of the geometry study in high school, in any case. And this brings me to this, I guess, key point, namely proofs are the foundation. And how are we going to study them then? How should we study geometric proofs? Well, here I'm going to offer you, I guess, 3 steps to learning geometric proofs. First of all, we need to understand the goal of the proofs. So previously, I guess in the previous example, when we were studying, when we were trying to prove negative of -1 is equal to 1, well, we need to understand the goal. Well, we are essentially getting rid of the 2 negative signs. And to do that, we need to understand what it means to put a negative sign in front of numbers. And so on and so forth. That's okay. That's the start of our proof. And in that example, we eventually found out, wow, we need to rely on some axioms. And that's when I introduced, what it means what's the property of this element 0, and what is the negative of another number. And secondly, when you are learning geometric proofs, the second thing is follow the format, okay? Follow the format. And this more concretely just means follow whatever your teacher writes on the board, okay? And lastly, practice, 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 okay? Because, of course, you need to practice to learn mathematics. And now we are going to look at, each of the bullet point in more detail. So what does it mean to understand the goal of proof? So in algebra 1, okay, in algebra 1, a lot of the problems are ultimately just solving equations. For example, how are we going to solve this linear equation? Well, all of you, of course, know how to do that. And the point is here, the answer is just finding certain numerical values. Okay, so here we're just trying to find a real number x satisfying this equation. But in geometry, the situation is kind of different because in geometry, the goal or the end result, the answer is actually given to us. So, for example, in this picture, we are told there's an isosceles, and we are told we are considering some kind of median, and the question is asking us to prove those two triangles, namely TAE or this triangle on the top and this triangle on the bottom are congruent to each other. And the result or the answer is actually given to us. Namely, those two triangles are indeed congruent. And when people see this question, they are kind of, be puzzled because yeah, they are congruent. What is there to prove? Well, that's precisely the point. We are actually connecting, so to speak, the conditions given, namely here, the isosceles stuff. We are connecting the conditions to the conclusions that we are asked to prove. And in this case, that means the congruence of those two triangles. And let me catch up on chat before moving on. Well, second bullet point was about following the format strictly. So here, what I want to emphasize is that in school, okay, when you guys take geometry in school, there's going to be this thing called two-column proof that you have to follow strictly to get full credit. And here is an example of a two-column proof, and you can see that this is actually very, very slow. So if you were to read this question a bit more carefully, in a little bit more detail. So here we are given that ABC is an isosceles and AC is the base, and the first two sentences, the first two statements given here, okay? Namely that there's a triangle isosceles and we have the base, and we are concluding that AB and CB, namely the two legs, are of equal length. That they spent two lines writing that, and you are okay in school. You are going to do that precisely as well. But and this is actually what's happening in Geometry Advanced as well at Think Academy. We do emphasize the two-column proofs format in Geometry Advanced, but this is simply a bit too slow for Geometry Honors because we are preparing students for AMC 10. And if you were dealing with a relatively difficult problem and you were to write down the argument in this fashion, then it's going to take ages to get the solution. And we do not want that. So to prepare competition, we will actually do without this two-column proofs. But it is our belief that if students can actually get a thinking process, the logic behind those difficult problems, then it should be relatively easy to adapt to this two-column proofs format as well. Okay. And lastly, the third bullet point about more practice. And at Think Academy, we actually provide all kinds of practices. So first of all, there are the problems in class. And for these classes, okay, for these classes, one thing that I really, really want to emphasize is you should take notes. Okay, take notes. See how proofs are written by teachers, because this is the way you are going to mimic. This is the way how you are going to learn how to write your own proofs. So this is the first source of, I guess, practice from the example problems in class. And then, of course, there are homework. Okay, there are homework problems. And then there are more practices in the form of workbook. Okay, there are lots and lots of problems in workbook, in I guess the workbook that comes with your textbook. And here the point is you should learn different models in geometry because there are some very common figures. Okay, there are some very common configurations of figures, I guess, and those. If you are familiar with those configurations, then it is very easy for you to recognize the kind of things appearing in competitions, for example. And lastly, also, our teachers all give relatively detailed feedbacks on your homework, and you should adhere to their word about their comments on your proofs, on your homework, and so on. And now I think that's enough yapping to you guys students. So here, this section is actually for I guess um parents as well. So I think I will give you guys maybe 1 minute to invite parents to here. So for those of I guess for those parents who are interested, I'll give you guys 1 minute to come here. I know. Not here? That's fine. That's fine. I mean, if your parents are not here, that's fine too. But let me just, give all of you guys 1 minute for you guys to invite your parents if they are willing to come here. Otherwise, that's fine. Why the skull emoji? That's fine. I don't really care what you guys send me, actually. Yeah, I wonder. Okay, okay. I know. Anyway, in any case, I think that's enough time waiting. Enough waiting. So, how can parents, help you guys? So, here again, I want to introduce, the think approach, the approach at Think Academy, namely, we actually teach students the format and the structure of proofs quite intensively. In fact, for geometry advanced, for example, we spend like 4 lectures on those two-column proofs and so on and so forth. For later lectures, because the materials are getting more difficult, and if we write out all the proofs in two-column style, it's going to take, again, a long, long time. Therefore, in later chapters, we actually do without with two-column proofs. But it is our belief that it is relatively easy for students to convert all their proofs to two-column proofs in any case. And secondly, well, at Think Academy, we definitely providing the practice problems in assignment and workbook, as people probably have seen in the previous slides. And lastly, I actually also mentioned this very briefly. Geometry advanced teachers will focus more on correcting students' proving steps. Namely, teachers are going to focus more on the formatting issues. And this is, I guess, slightly different from geometry honors, which where teachers actually care more about the steps of the logic, I guess. And here, once again, this is also something that I mentioned very briefly, namely for geometry advanced, we spend quite a long time on formatting issues, namely the two-column proofs format. And in fact, we spent 4 whole lessons on that. Okay. And lastly, just to reiterate how students can contact their teachers, well, we have this great parent app, namely, and on this parent app, you can actually contact the teachers teaching your actual children, I guess, directly. And we highly recommend that you download it because not only can you contact the teacher directly, you can also ask for one-on-one services, and you can also, for example, I guess, contact customer services for other logistic issues, for example, rescheduling, for example, transferring, and so on and so forth. And here on screen, I have listed the QR code for downloading parent apps. Yeah. Okay. And thank you. That's actually all I have for today. And this is the QR code for our teacher Yao, who's actually managing, I guess, the geometry grade. And now, if you have more questions, you can ask. And this is essentially a Q&A section of the talk. Okay, people, you guys are enjoying your spamming, huh? Yep, you're welcome. All right. If you don't have any more questions, you are free to go. Otherwise, um, ask your questions, I guess. Yeah. All right. Thank you. Thank you for coming, and you're welcome. Yeah, no worries. All right. Any questions for me? I'm not seeing the questions. Maybe they're buried in the spams. Let's see.
哎，赵东老师啊，
Yeah. Hey, hey, 你好. Hey.
哎，赵东老师，我想就我们家孩子的这个目前学几何的情况，问一个问题。
您说。
是现在我们家孩子在那个几何的 honors 班，他已经上了2节课，就是之前的小学呢几何稍微学了一点，就是在学校里面那样学，也没有上过什么课外班，所以他几何基础不是太牢。那他上第一节课那个 parallel lines 的时候呢？他其实原来代数的课他也上过，包括现在代数春季班的课，其实我觉得后面都挺难的。他当时上的也觉得好像都可以接受，但是上那个第一节课 parallel lines，他说我怎么从来就没上过这么都听不懂的课？
那是吧？
那在我们看来，上那些东西好像还是就是基础知识稍微拔高一点。然后然后后来我就跟他把作业啊什么的就都跟他讲了一下，他又上第二节课，上第二节课情况好一点了。现在今天刚刚在做那个第二节课的作业，做第二节课的作业呢，他呢就是说他基本上那些题他都还是有思路，而且思路也是对的，但是他没有自信心，他就做一个字，他说我是不是错了呀？他就会这样想，然后他到了后面，因为小学他也没上过学而思，也没上过课外班，他有的时候会有一点计算方面的低级错误。他的情况整个就是上了2节课，整个就是这样。我觉得比他原来代数的情况呢，好像要差一些。就他的这个情况，我反映给您，您觉得是应该怎么样去有针对性的去提高呢？
明白明白，这个就是学生对于自己写的证明不够自信，这是一个非常怎么说常见的问题。因为就是学生总是会想这个东西这个结论到底能用还是不能用？这个其实我是刚才也是提到过这个每写一步的时候，学生总是会怎么说 second guessing themselves，这样因为觉得这个结论如果是对的话，那这个题是不是太简单了？这个结论是不是我应该不能用？如果不能用的话，那我应该又用什么？这个位置呢，我们给出的这种就是叫什么rule of thumb，这样的话就是说，如果说想要用的结论就是老师没有在课上用到过的话，那就不应该用。要用的是什么样的结论呢？就是说老师在课上用过的知识，比如说在第一讲上讲平行线的时候，老师用的东西是什么？就是内凑角或者说同旁内角互补，或者说内凑角相等这两个主要的思路。那么在回答问题的时候，就是在写自己的证明的时候，所有的步骤的话，应该也是围绕这两个重要的定理或者说公理来进行的。如果说他的那个证明是围绕这两个东西来进行的话，那么那就是可以的，那就放心大胆的往下写，是这样子。
哦，我想起来了，他就第一节课上下来，他情况不太好嘛，他是怎么回事呢？第一节课就是刚刚您在回答我前面这个问题的，就是讲的时候，我就想起来了，他是怎么样的？不是说一对平行线被另一条直线就是一对平行线，就反正是另一条直线就截了之后，它就有2个交点，那反正就是基本上是这个模型，就是这种简单的模型呢，他们其实好像4年级的时候在学校学过。 基本
嗯，
上也就是那种非常基础的题让他们做一下，所以它其实简单的模型，它基本上还知道的什么几个内错角啊，除了它那个英语的名字跟中文名字有点对不上号以外，它基本上还知道的。但是
嗯，
呢，那个作业题包括老师上课的例题呢，实际上一个图形里面它可能有好几对，就是这个
对对对，嗯
题其实是把这个基本的这个知识其实复杂化了。这个时候呢，孩子好像就糊涂了。那这个时候呢，就得然后呢，我再给他，因为他作业他就很糊涂，没办法，我只好跟他讲一下，我就把那个，比如说三角形里面它有一个这样的模型，我就把这个模型专门的画出来，然后呢就画在边上，就让他一个个字母然后去对，一个个字母去对，对之后他才明白哦，原来这个模型用在这个图里面，他好
嗯。
像就是被就在这里他就被困住了，我就感觉好像
明白明白。那这个位置可能是的确，我们因为课程的速度是的确比较快，所以说就是我们有时候没有强调，比如说像您讲到的，就是什么样的角叫做内缩角，什么样的角叫做什么同旁内角，然后学生可能没有什么经验，所以说图形稍微复杂之后就觉得是不是没有内缩角或者没有同旁内角，但是它到处都是，对吧？就所以说学生容易糊涂。这个的话，其实我们觉得话是通过做题，就是通过多看题目的话，多看图形，那这个是可以掌握的。所以说，这个在第一节课上就是有这种问题是很正常，我觉得是不用太担心的，因为图形接触多了，题目做多了，这个孩子经验起来之后，这个就不会就自然而然不会有这个问题了。像您说的这种。
哦，好的，那看样子还是要把这
嗯。
些暑假花点功夫把这些作业啊练习尽量的都做好，
嗯，
谢谢。
对对对，是这样。像您刚才那个做法其实也很好，就是把那个最基本的图形就摆在旁边，然后孩子可以对着这样看，那么就是孩子就知道什么样的角是内缩角了，对吧？但是我不知道这个是可能就是具体的细节的问题啊，就是您刚才说是把那个三角形的东西放在那个比如说讲平行线那一讲的上面，那可能是其实是有点小问题的，因为三角形方面的知识呢，在讲平行的时候我们还没有讲到。这其实也是我就是之前那个讲座上面说到，这个我们还没有学到的知识就不要用，对吧？因为如果说我们还没有学到三角形，那么我们这个图形之中虽然有很多的三角形，有些性质也不要用，因为这个位置的重点呢是训练怎么样识别平行线，怎么用平行线的方式来证明就是题目所要求的东西。那么这个时候呢，就想点怎么说呢，就是想点别的方法，然后就是摆脱这种对于三角形的依赖，这样子做题。当然这只是一个小非常非常小的例子，就是说一下。
另外，我觉得好像就是老师上课用的一些方法，比如说他用不同的角去比如说它不同的几何，比如说两条线平行吧，它就会有一些标记。然后比如说我某个角我要求它，可能就用一个有颜色的一个东西把它标注出来。我觉得可能
对对的
就是这个就把那个图形好像跟那个 coloring，就是那个画画的 coloring 结合起来。可能。
啊。
也是一种学几何比较好的一个方法，就是说，
嗯，对对对，这个的确是，当然这个是因为上课的时候我们有这个条件嘛，但是学生自己做题的时候，可能这个就稍微复杂一点。这个时候我们可能就推荐，比如说画一个小的角度，或者说画两撇这样子来表示那种角度，是吧？这个其实我们课上的时候其实也会用到这些符号，当然颜色可能是孩子更喜欢的方式，所以说我们也会用到，是这样子。嗯。
嗯，对，它这个就是基本上是这个文字和图形要结合起来思考问题，自己要做一些 mark，可能
嗯嗯。
写几何题的时候还是很重要的。我觉得这个
对对对，这种 mark 像您说的这种标记的话，的确是非常重要，因为就是不然的话，不停的图形和文字眼睛两边转的话，其实也是挺累的，而且这有时候也记不住，对不对？但是在图像上标注之后，那就比较直观一点，那就知道这两条边是相等的，或者这两个角是相等的，这样的话会更有帮助，是这样子。嗯
对对，好好，谢谢你啊。
嗯，好，没事，好，应该的，嗯。All right, any more questions for me? All right, I think I will actually end the lecture here. Thank you all for coming. Thank you. That was a good crowd. Thank you.